for introduction. Let me first thank the organizer, Chareyre and M&MoCS, and the nice city of Alpino. So I'd like to speak a little bit of conceptual modeling today, because usually we are deeply rooted in some conceptual models, so deeply rooted that we forget that we adopted it in the first place. For granular materials, it doesn't matter, we all know everything very well, but if I speak of fluids, it's less clear, and I will propose a new kind of conceptual model for simulating the fluid in granular materials. So I will introduce the main ideas of the talk, and I will try to go relatively quickly in the first part, which is a numerical implementation of a particular conceptual model, in order to keep time for the last parts, which are examples of applications of this particular implementation. Don't hesitate to stop me at any point if you want to discuss something. So this is a granular material. I cut a cube in it. This is the conceptual model already. We have solids interacting with each other. And I will mention three types of scales. We have the micro continuum scale. I can say each body is, for instance, a linear elastic object. Or I can think about the macro continuum scale, in which this cube is a point, and then I define bulk properties for it. And there is an intermediate scale, which is the grain scale that you all know very well, which is to say that, okay, I define degrees of freedom for one grain. So what Kendall did when he proposed this concept was, okay, if we start at the micro continuum scale, we can study the interaction between two elastic spheres. It will result in Hertz theory of contacts. If I put in addition to that friction between the surfaces, I have Hertz-Minlin theory of contact. And from this theory, I can write a relationship between the forces between the objects and the motion in terms of degrees of freedom of each object. Usually this is called, maybe not usually, in many cases this is called the vision of rigid grains with deformable contacts. I in fact don't like this naming really much, because I think it is in fact a model of deformable grains, and that's it. Simply, we don't see the details of the deformation near the contacts. They are hidden away, and they are contained in the contact law that we write. But we can associate to this free energy whatever we like. There is no difficulty. Just we put all the complexity in the interaction equation. And so this was the idea of Kendall decades ago, and it resulted in the most cited paper in geomechanics. So this, obviously, it was a brilliant idea, and what I suggest is we should see if we can reproduce this kind of conceptual modeling for the fluids, because if we can do that, we can compute very large systems. We can include quite a lot of physical effects at a very low price in terms of equation and computational power. So let's see what we can do. So if I give you this picture and I ask you to count the number of particles, so you will probably all of you give the same answer. If I give this to you and I ask you what is the number of pores in this picture, I have probably the same number of answers than in the room, and so this is quite a challenging topic to associate to this something that is at an intermediate scale, not at the scale of the micro continuum inside the pore space, and not at the scale of this cube, which is too large, and we will lose all the physics. So I will propose something to define pores in this thing. Interestingly, the idea is not very new. They do that a lot in hydrogeology in what they call the pore network models. The thing is that for them, this would be the pore space, because they want a simple topology for the pore space. So for them, this would be the fluid domain. The solid domain is quite complex, but they don't care because it is a rigid matrix, and so they are not interested in that. So, but I start from the granular material, so I have to deal with this. This is the pore space. So, classical example of this concept of upscaling a little bit is the model of the pendular ring between two particles. It has been applied by many. And this is a good example of how you can start from the micro scale, use Laplace-Young, and deduce something that will link volume of the bridge, force applied by the bridge to capillary suction, for instance. But I will speak of saturated one-phase flow. First, some results at the micro-continuum scale. If you solve the Navier-Stokes equation in a three-dimensional sphere packings, you impose a macro-scale gradient and the fluid flow through the problem. You have here velocity field and the color is the pressure gradient. You have, of course, at the macro scale gradient of pressure. If instead of plotting the pressure gradient, you plot the field, if instead of plotting the pressure field, you plot the field of gradient of pressure, you find that overall blue is nearly zero, so you have no dissipation in the large voids. Red is the maximum gradient, so you have strong pressure gradients near the neck of the flow path. No surprise. But I will use this property to say, okay, this is one pore. Basically, this is the idea. So how to define that in a simple topological way? You use triangulation. Niels Kreutz mentioned that in the morning. You do a triangulation of the sphere packing and you find that each facet in the triangulation between two tetrahedra corresponds to a location where you may have strong gradient in the pressure field, and inside one element basically there is no gradient. If you approximate this by a piecewise constant pressure, it's not that bad. So let's do that. How can we write equation now on this kind of mesh? First, at the micro-continuum scale, you have a continuity equation. I assume incompressible phases. So mass conservation becomes a volume conservation equation. I write it in an element. It says that the sum of fluxes through the boundaries is zero. But this is this equation. But I can replace the fluid velocity by the relative velocity of the fluid, U star, relative to the solid phase. So now if I do that, I have a relationship between the relative fluid velocity and the rate of volume change of the element. This is tetrahedra. Remember that it has the vertices at the center of the particles. So if the particles move, this tetrahedra is changing in shape and volume. So here I have a balance between the movement of the particles and the flux of fluid. Next, if I assume a Stokes regime, no turbulence, I can reasonably say that the flux between two elements is linked linearly to the pressure jump between element I and J. Let me write this. Now the question is, what is K? I will not enter the details, but you can define K started using the topological property of your two pores, and this is the only constitutive relation in the model. All the rest is first principles. So you can define K somehow. I will show a validation later. If you do that, now you link the pressure to the movement of the particles. This is for one pore. You have four fluxes through the facets, and this is the motion of the particles. Write this for all the pores. You have a big linear system to solve. By solving this system, so this is the deformation rate of each pore, boundary conditions, this is an unknown pressure field, and here permeability matrix. You solve this and you have the pressure field as a function of particles' velocity. From the pressure field you can deduce forces applied by the particles by integrating pressure and viscous stress. Okay, and you result in a system to solve. What I want to show is that there is an obvious parallel between this thing and the continuum scale. At the continuum scale you have mass conservation. The divergence of the fluid velocity is Laplacian of pressure is the change of fluid content in one point. You have momentum balance, written here in the assumption of static equilibrium. This is what you find in Bio theory of poroelasticity, and in our model we have rate of change of one pore, here different gradient of pressure integrated on the boundaries. equivalent to this equation. Here you have sum of contact forces, drag forces, weight. Here you have gradient of effective stress, gradient of pressure, weight. So it is exactly the same. In fact, if you take bioporoelasticity, you write it down using finite element method, for instance, you will end up with a linear system of equations exactly the same than the one I'm solving. The only thing is that defining the continuum scale permeability that would match the one that we have at the discrete, at the micro or at the grain scale would be very tricky and not very useful, but formally the mathematical problem is the same, and so we should be able to validate our model by finding some classical results of poroelasticity. So I will show that later. This is just a validation of the constitutive relation defining the permeability locally. We made permeability measurements in mixtures of glass beads of different sizes. For instance, here you have small yellow beads mixed with red, big, large beads. And depending on the fraction of small and big beads, you measure a different permeability, and you predict it with the numerical model. The experiments are the dark dots, the simulation gray dots. It's not perfect. There is sometimes a ratio of 2 between the experiment and the simulation. It's not perfect, but not that bad. At least much better than the famous Kozeny-Karman equation, which is the pink one. Less good than the very old empirical equations that you find in some soil mechanics books, which fit the points very well. So, okay, we have the correct order of magnitudes at least, and if we have a change of porosity, for instance, it will be reflected as a change of permeability spontaneously in the model. Now, let's see if it works if we simulate a one-dimensional consolidation problem. I don't think I have to summarize what is a consolidation problem. So you impose zero fluid pressure at the top and at the bottom. You impose an increment of stress on the top of this REV, let's call it. You look what happens. Dots are the simulation, solid lines are the results of the Terzaghi problem, and you see that it's exactly the same. For short times you have the fluid pressure exactly equal to the applied load increment. With time the pore pressure is dissipating, the fluid goes out, settlement occurs, pressure goes back to zero, and it's exactly at the same rate as in the theoretical solution. It's even surprising that it is so close, because we don't have a uniform permeability in space, we don't have uniform elastic properties, but still with a few thousand grains it works perfectly. Okay, so you may think, what is the point of finding results of linear poroelasticity? We know all that already. We don't need a granular model for that. But there are so many special cases where something is more complicated. For instance, for one, permeability is a function of space and time if there is a deformation. Elastic properties are a function of space and time. It's not even elastic, it's in fact elastoplastic. In compression there is something, but in traction there is nothing. And so, for instance, you have liquefaction due to this nonlinear behavior of the solid part. So now let's say we do something. Again, it's one-dimensional. Instead of applying a load increment on the top of an odometer, you have a submerged column of particles, and the top boundary condition, it's a free surface in terms of stress on the particles, but you can impose the fluid pressure. First step, loading. At time zero, you increase the pressure of the fluid at the free surface. There is a bouncing. For short times, you compress the column. By the way, the fluid is compressible in this case. So for short times, you compress everything. And as time goes on, the skeleton will bounce back and you will equilibrate pressure. This is the comparison between simulation and theoretical analytical solution. Again, it fits perfectly in terms of evolution of pressure in the column. So that's okay. Now imagine that it's not a step function. You impose a fluctuating value of pressure at the free surface. And so you create waves inside the column with a shift of the period and the damping as you go deeper into the column. There is again an analytical solution for that. The solid line and simulation the dotted line. The interesting thing is that at some point you can have a pressure in the fluid which is larger than the total weight of the column, and so you should have liquefaction. In the analytical solution, which is based on linear elasticity, it results in a traction in the skeleton. And if you know granular materials, you say this is nonsense. You cannot have traction in a granular material. In the paper where they reported the analytical solution, they were smart enough to start the plot of effective stress versus time at 0. So they hide that part where the effective stress is actually negative, traction. But still they use a solution where it happens. They just don't plot it. So in our model, of course, there is no traction. The grain can split and float for a limited time period. And so we have this. It's not exactly 0. And it means that there is a delay also in the liquefaction process. So this is the kind of thing that you can gain from using a granular material. You don't do a lot of constitutive assumptions, and you can simulate quite complex process. I think I will skip this because how much time is left?
You have spoken 17 minutes.
17. Okay, so I will just show the video. Another quite non-linear and complex case of coupling. You inject a fluid below a box containing particles. This is a three-dimensional problem, but you cut it in the middle to see what happens. So you create this kind of bubbling in an elastoplastic material by injecting the fluid. You can imagine that the field of permeability is changing quite a lot in this problem, and again, it's something that you can do with this new model. So I shift this and I go to suspensions. There is something that you will never derive from classical poromechanics. It is the bulk viscosity of a mixture of grains and fluids. Because bulk viscosity is independent of Darcy's equation. It's not a problem of permeability. This is something we want to put in addition to the coupling I showed before. It is something relatively well known that in dense suspensions everything is dominated by the lubrication terms describing the force between two close neighbors due to the presence of fluid between them. Here you have four expressions of force linked to the force and torques linked to the different possible relative motion, normal displacement, twisting, pure shear, and rolling of grain. So you can associate forces and torques for all those effects. And you implement this in the model and you try to simulate suspensions. So we did that with a PhD student recently, Donia Marzugi, and I will show you some results of what happens when you simulate the simple shear of a granular medium with first the coupling that I've shown before, plus the equation coming from lubrication expressions of forces and torques. So what is special in our case, we include all terms from the lubrication derivation. Usually people include only the normal one because they say this is the dominant term. We put all of them. We say that we can have at the same time lubrication effects and solid contacts. In many cases people say there is never any contact when there is a fluid. It's not possible. I will prove that wrong later. And we have the coupling. This is what you get. So you impose a shear rate and you deform. This is 1000% of deformations. Okay. So evolution of stress. This is this. On the right hand side you have the zoom. So evolution of stress with total deformation. You have a peak. It happens at the same time as you have a dilatancy in the early stage. When you have dilatancy, you have a negative pore pressure, a suction, which tends to keep all grains together. With time, pressure here goes back to 0. And the shear stress reaches a constant value. If you neglect the coupling with the the pore scale fluid, you don't have you neglect the pore pressure. Basically, this is what they do usually in physics when they use lubrication. They say there is no volume change. If there is, we don't care. So they don't have the coupling with pore pressure, which is in fact quite important. If you do this, then you don't have the same peak. Okay, so the fact that you have suction at the early stages gives you a higher peak in the shear stress. And this is due to the negative pressure. So at that point you may think, okay, it looks exactly as critical state framework for soil. I have the latency initially and then I reach a plateau. But it will become more fun if you plot the porosity, or here in fact solid fraction, 1 minus porosity. You find that at the critical state, let's call it, or steady state, at the steady state, porosity depends on the shear rate. So you have a critical state theory depending on the shear rate. So this is the kind of funny effect that you have when you do that. This is the sample. Okay, so periodic boundary conditions, let me go back. So it will start from the very beginning, pressure equals 0. Red will be excess pore pressure, blue will be negative pressure. Initially you have the latency, so negative pore pressure, blue. After that I will accelerate, so it's blue again. And then I slow down, positive pore pressure. I have a transient liquefaction phenomenon as soon as I slow down the motion. So I can repeat that as many times as I like. So each time you change the shear rate, you have a response in terms of pore pressure. The amplitude of that depends on the problem size. This is a coupling. It's not a constitutive relation that can describe this. So let me skip that. The point is only that you can define shear rate is a non-dimensional way, but this is relatively well known. But our important thing, our suspension model fits perfectly the empirical law that they deduced from experiments. It's finished. It's finished. I have still 3 minutes.
No, including the question.
Yeah, okay. Oh, that's good, that's good. So this solid line is empirical line going through the data points of Boyer and others, and the dots here is the shear stress that we measure as a function of the shear rate. So it works very well, and this is due to all the assumptions that I listed, or features of the model. Lubrication plus solid contacts. If you take only one, it doesn't work. All terms in the lubrication. If you take only the normal lubrication, it doesn't work. Coupling, this is another thing. Physicists, they don't care about coupling. Transient state in the beginning is an experimental artifact. They never looked at that, but the thing is that we can simulate it. And for us it's very important, because imagine a debris flow going down a slope, and the slope is changing, the slope angle. So it's accelerating, decelerating, accelerating, so it's always transient. So you have a major effect of this coupling. I'm done. So we do many applications of this pore scale concept at the moment. Some of them are hydrofractures, swelling, superabsorbance, beads of polymers, different things. Next steps for application of these concepts are to include the dynamic two-phase flow. Tomorrow you will see a talk of Chao Yuan, who will extend the pore scale to two-phase problems. Inertia of the fluid is also a challenging question. And if you like to try this, you can freely get it. It's part of an open source project, so everything can be reproduced independently. You can download it and try it. Thank you for your attention.
Thank you very much for nodding. A few questions. Yes, the first part of your talk, the pore scale approach. Did you compare to pore network modeling? You mentioned that.
Yeah, basically this is a pore network model. The problem is I have a pore topology that is much more complex than what I do. They do the stick and ball.
Yes.
So that's why what I wanted to say when they stick and ball. This is the ball, this is the pore, and the stick we don't see it. it is somewhat. So the thing is, they never really solved the problem of this kind of pore space, but the concepts are exactly from pore network models. The only thing is, I have a deformable matrix, and this is also another difficulty.